So, good morning once more. Welcome to today's training. Today we are going to look at a very interesting protocol, the protocol by the name OSPF, Open Shortest Path First Protocol. As we might have mentioned when we started learning about routing in the previous topic, OSPF is one of the dynamic routing protocols. Meaning that it's not configured manually by the network administrator, but really it has its working mechanism to ensure that it can be able to work on its own. So in this topic, we're going to understand how this dynamic protocol is able to learn or generate routes on its own, and also be able to respond to topology changes in case there's a link failure, for example, at any particular point of the network. So I'll start by reading the foreword. So as we all understand so far, static routes are manually configured. We've so far configured static routes, floating static routes or backup static routes, and also default routes. So even network topology changes, and when you talk about network topology changes, it means there is a failure in the network topology. Either a link goes down, an interface goes down, or the device itself goes down. If that happens, static routes have to be manually adjusted, which restricts the large-scale application of static routes on the live network. So if you have a large network, then it's not possible to use static routes. Dynamic routing protocols are widely used on live networks because of their high flexibility, high reliability, and easy scalability. So those are the advantages. Easy scalability. So the open shortest path first protocol is widely used as a dynamic routing protocol. Widely used, please note, widely used. So this course describes the basic concepts, working mechanisms, and basic configurations of OSPF. By the end of this chapter, you should be able to. Anthony, please help us with reading out the objectives. Anthony, are you there? Can Bor help us if Anthony is not ready? Okay, Morris?
Yes, I can read. Can
Thank
go
you.
on. Yeah. At the end of the topic, you'll be able to describe the advantages and classification of dynamic routing protocols. The second point, you'll be able to describe basic OSPF concepts and usage scenarios.
Yes.
The third one says you'll be able to describe the working mechanism of OSPF.
Yes.
And lastly, we'll be able to implement basic OSPF configurations.
OSPF configuration. So that is what we're going to be doing in this particular chapter. Okay. So let's begin with an overview of OSPF. An overview of OSPF. So as we've already mentioned, static routes manually configured and maintained. The advantage of static routes, command lines are simple and clear, but they only apply to small scale or stable networks. That is when you have very few number of routers. The disadvantages of static routes, So it cannot change, it cannot adapt to changes. So as the number of devices increases, also the configuration workload increases sharply. Because you have to manually configure each static route. You add a device, you have to configure it. So when we were saying that dynamic routes have the advantage of scalability, it means that you can be able to add more devices quickly, because you won't need to do a lot of configurations. You'll only configure the OSPF process and the networks to be advertised on that particular device. So that's the problem again with static routes. Then it's unable to dynamically respond to network changes. So if network topology changes, they cannot automatically converge. So static routes must be manually modified in case there is a failure. In case there is a failure in the network. So you see here, if in this particular example, as you can see, you've configured a static route to a network in R2 from R1 to R2. Now, in case this link goes down, if this link goes down, then you have to manually reconfigure an alternative route, maybe through R3 to R2. That is if you had not configured a backup. So those are the challenges when dealing with static routes. Okay, so to cater for these problems, then they created what we call dynamic routing protocols. Dynamic routing protocols are classified in one of two ways. One of them is by the autonomous system, AS. And the other day I told you, just think of an AS, for example, as an ISP, where we have a group of routers that are operating using the same routing principles or policy. So if all of them are using OSPF, for example, or ISIS, so most likely all these routers are owned by the same organization. So you can think of an AS as an ISP. So we have dynamic routing protocols that are used to interconnect autonomous systems. So those ones that are used to interconnect autonomous systems, they're called exterior gateway protocols, EGPs, because they're used to import external routes from other autonomous systems. So that's why they're called exterior gateway protocols, because they import external routes. So one of the examples of such a route is BGP, Border Gateway Protocol. Then we have dynamic routing protocols that are used within the autonomous system. One of them is OSPF, and these particular routes are referred to as interior gateway protocols because they are used within the autonomous system. We have one called RIP, we have OSPF, and we also have another one called ISIS, intermediate system to intermediate system. Intermediate system to intermediate system. The other classification of dynamic routing protocols is by their working mechanism and algorithms. Their working mechanism and algorithm. So one of them is called distance vector protocol. With distance vector protocol, the main metric that is used is the distance between the source and the destination. So the shortest distance between the source and the destination is used as the optimal path to the destination. And when you talk of distance here, most of the time, for example, with RIP, we are talking about the number of hops or the number of routers that we are going to pass through. So if we have two paths towards the destination, and one path passes through two routers, and the other path passes through four routers, then RIP will choose the path that the packet is going to pass through to routers. Is that clear? Yeah. So that's why it's called a distance vector protocol. Then the other type of routing protocols is called link state routing protocols. So by link state, this one looks at the state of the link using metrics such as the link bandwidth, for example, what we're going to be calling the cost when we are dealing with OSPF. So OSPF, ISRS, both of them are link state routing protocols. Now, there's one we have not mentioned. The one that we have not mentioned here is BGP. Now, BGP uses what we call the path vector algorithm. The path vector algorithm. Now, the path vector algorithm is just a variation. The path vector algorithm is a variation of the distance vector algorithm. So that's why I'm putting it close to that. So BGP uses a protocol or algorithm called path vector algorithm. Okay, so let's just have a brief about distance vector protocols. So as I said, a router running a distance vector routing protocol will periodically flood routes. Meaning simply flooding routes, saying, if you want to go here, look here, if you want to go here, then you need to go through R2. So everyone is sharing their routing table with the other person. Are you getting the point? This is how to go here. This is how to go here. This is how to go here. So everyone is flooding their routes. So when they do this, then each router is going to install the routes that have been flooded into their own routing table. So you are told this is how to go here. This is how to go here. So you'll only follow that direction. Are you getting the point? This is how to go here. So each router on a network is clear only about where the destination is and how far the destination is, but unclear about the whole network topology. So as you're going to see, with link state routing protocols, then the routers are going to be aware of the network topology. How? You're going to see just in a short while. So in summary, this is how distance vector routing protocols really operate. Now, with link state, they do what we call link state advertisement. That is what they're calling LSA. LSA flooding. Link state advertisement flooding. So how does this happen? First, the routers establish a neighbor relationship. We're going to see how. After establishing the neighbor relationship, then they go ahead to exchange link state advertisements, LSAs. Now, so look here, the difference between distance vector and link state routing is that here we are sharing the state of the link, while in the other one we were sharing the routes, we were sharing the direction, how to go. But in link state routing, we are not sharing really the direction. We're just advertising the link. Now, what does an LSA contain? A link state advertisement describes the router's interface status information, such as, for example, the cost of the interface. And by cost we mean the bandwidth, for example. Are we together? So other than that, we also advertise the connected interface name and things like the network to which that interface belongs to. So we are not really advertising a particular destination, how to go to a particular destination. We're just advertising those different links and the networks they belong to. Then each router is going to finally calculate their own path to the destination. So that's the main difference with this. So you're going to see that if you configure OSPF on all these routers, then they're going to be, on each link, they're going to be exchanging link state advertisements. Are we together? Are we together? Yeah, they're going to be exchanging that. Each link state advertisement is going, for example, to advertise the cost. The cost is calculated using what you call the reference bandwidth, which you're going to see in a moment. But really, it relates to the bandwidth of the interface. Are we together? Eh? Yeah. And listen here, we are saying bandwidth of the interface or cost of the interface because when you see 100 megabits per second here, it doesn't mean that this link can transfer with 100 megabits per second. It simply means that this interface can process packets at 100 megabits per second. Are we together? And normally, when we are interconnecting devices, we interconnect devices on interfaces that process using the same speed. You getting the point? Because if we interconnect a 1 gig link to a 10 gig link, then we are going to have data loss on the 1 gig link. Because this guy is going to send at very high rates, and this guy cannot be able to process at those rates. So we're going to experience data loss on the lower gigabit link. Are we together? So anytime you see a 1.5444 megabits per second, it doesn't mean really the link. It means the interface. This interface and this interface can process data at that speed. Is that clear? Okay. Now, the other important concept when it comes to link state routing protocols is what we call the link state database. Link state database. So when you receive an LSA or a link state advertisement, you save it in your own link state database. In short, we will be talking about LSDB. Then when we are talking about link state advertisements, we'll be talking about LSA. So link state database. So routers learn the whole network topology through the LSDB. So the router stores in LSDB, LSAs in LSDB. LSDB will contain the description of all router interfaces on the network. Are we together? Each LSDB will contain information about all the interfaces that have been configured to communicate on that OSPF process. Is that clear? Huh? Meaning that, for example, on router 2 will have information about that link. It will have information about that link. It will have information about not link but interface. That interface, it will have information about that interface. It will have information about this interface. It will have information about this interface here, about this interface here, and also about this interface here. Is that clear? Yeah. Now, the link state advertisements, other than the cost, other information that the link state advertisement contains is, for example, the relationship, sorry, relationship with other routers or interface. And also, it might contain information about the neighboring what? The neighboring routers. So we are going to see the kind of neighbor relationship that we can have when we're dealing with OSPF in a short while. Okay. Now, OSPF uses an algorithm that we call the shortest path first algorithm. Shortest path first algorithm. Shortest path first algorithm. Now, we have said that the LSDB will contain information about all the interfaces. Now, from this information, each router is going to calculate their shortest path tree, something we call the shortest path tree. Each router is going to calculate its shortest path tree with itself as the root of the tree to all the destinations in that network. To all the destinations in that network. At this particular level, you are not taught how to calculate the shortest path tree. But if you look at my videos on HCIP, on OSPF, you're going to understand because I describe, and that content is there on HCIP level, how the shortest path tree is actually created by the router. But at this particular level, all you need to understand, for example, is R3 will use its LSDB to, number one, it's going to select itself as the root. Then find out, hey, if I need to go to router 2, this is how I'm going to go to there. If I need to go to router 4, this is how I need to go. If I need to go to router 1, then the best route is to go through router 4, then I go to router 1. I think this was a mistake. I think maybe this was supposed to be, okay, I really don't know the numbering, how they did the numbering here. But are you getting the point? That you get all the routes, then you calculate the shortest path to each of the destinations using what we call the shortest path first algorithm, which creates the shortest path tree, SPT. Okay, so really that is how this works. So once you've calculated this, now you're going to install this because they are the shortest path to each of the destination. You're going to install this in your routing table as the optimal path. So we're simply saying that when R3 has a packet that is supposed to go to R2, maybe it will just send it like that or something. If it has a packet that is supposed to go to R4, maybe it will send it like that. If it has a packet that needs to go to R1, it's going to send it maybe through R4 and maybe send it here. So everyone creates their own routes to different destinations. Are you getting the point? Unlike distance vector where we were sharing the route. Here we don't share the route. We just share the networks and the link state. Then you calculate how to get there by using the cost, really. So that is how SPF calculation is done. Okay, so after calculating SPF, then what happens? It generates the routing table. So the router installed routes for the calculated preferred paths into the routing table. So based on SPF calculation results, each router installs routes into the routing table. So those will now be used as the optimal paths to the destination. So far, Number one, we said it begins by, actually, it begins by this neighbor, forming neighbor relationships. Then number two, LSA, we flood LSA, LSA flooding. Number three, we do what? We save the LSAs in the LSDB. Eh? Save, save LSA in LSDB. Then number four, calculate what? Calculate SPF, right? Then number five, install optimal paths in routing table. Yeah. Yes, please, Luya. Question? Mm-hmm. Exactly, exactly. So Luya is asking, what if the what if the shortest path, like this is the best path from R3 to R4, what if this path goes down? So as he has correctly mentioned, each router will have to recalculate their shortest path tree. Are you getting the point? They'll have to recalculate their shortest path tree. All the routers, just because one link has gone down, they have to recalculate their shortest path tree and thereby find the new best or optimal path to each destination that is currently available. So that is correct, Luyo. Okay. Okay. So again, just a summary of what I had just typed there. So step number one, we establish neighbor relationships. Step number two, we do what? We share link state information, LSAs, link state advertisement. Step number three, oh, sorry. Oh, in step number two here, they have also included saving the link state advertisement in LSDBs. Then on step number three, you calculate using the SPF algorithm the best route to each destination. Then step number four, we go ahead and save the best or optimal routes in what we call the routing information base, RIB, which is now the routing table really, routing information base. So don't forget this, by the way. I think it's important that RIB stands for the routing information base. Okay. So an introduction to OSPF. So OSPF typical link state routing protocol, widely used, look here, widely used IGPs in the industry. So most likely in that organization which you're going to work in, you're going to be using OSPF. I like these notes because at the end of it, they show you where exactly you're going to be implementing on the network topology, hierarchical network topology, where you're going to be implementing OSPF. So most likely in the organization that you're going to work with, you're going to be configuring OSPF. Let me just mention that while OSPF is used in large organizations, most of the time, ISIS is used in even larger organizations like ISPs. So you'll get that ISIS is mostly used by ISPs. Again, I've covered the concepts of ISIS and configuration in my HCIP video tutorials. So in case you want to learn further, you can go and have a look at that. Now, so far, we have two versions of OSPF. OSPF version 2, which is the OSPF that works with IP version 4. Then we also have OSPF version 3, which is the version of OSPF that works with IP version 6. So in this particular chapter, when we talk about OSPF, we will be referring to OSPF version 2. Are we together? The one that deals with IP version 4. So we're not going to be looking at OSPF version 3 in this particular chapter. Now, normally, RFC, when you get this RFC 2328, these organizations that work on these protocols, like the Internet Engineering Task Force, normally they do what we call a request for comments. So these requests for comments are the ones that the community use in order to combine their knowledge and come up with how a particular protocol is going to be operating. So anytime you see RFC, just know it means request for comments. So OSPF routers will exchange link state information. Look here, but not what? But not routes. So we already have discussed that. So link state information is key information for use to perform topology and route calculation. OSPF routers also collect link state information on a network and stores it in the LSDB. Routers are aware of the intra-area. Intra-area. When you see intra-area, it means within an area. Intra-area. We're going to see something small about OSPF areas and be able to calculate loop-free paths. Loop-free paths. So there's also an issue of creating loops when you're configuring OSPF, especially among multiple areas. So we're going to see some of the strategies that are used to avoid having loops. So each OSPF router uses the SPF algorithm, shortest path first, to calculate shortest path to specific destination. Shortest path. The routers will then generate routes based on these paths and installs the routes in the routing table. We have already said that. So SPF supports what? Variable length subnet mask. Simply meaning, with OSPF, you can still use the variable length subnet mask instead of the default one, /8 for class A, /16 for class B, /24 for class C. So you can use /23, /32, /30, etc, etc. Is that okay? So multi-area design enables OSPF to support a larger network. So we are going to understand how. For now, just put that in your mind, that because we can be able to calculate multiple areas, that's what they're calling multi-area, then we can be able to scale our network. We can be able to scale our network to expand and become bigger and bigger and bigger. And that's one of the advantages, by the way, of OSPF compared, for example, to RIP. If you read a little bit about RIP, you're going to notice that with RIP you can't be able to do more than 15 routers, if I'm not wrong. So if you're having 16 routers, you simply can't use RIP in that kind of network. But OSPF, ISIS, it can grow even up to hundreds of routers. Okay, so this is what I was telling you. Where do you configure? Where do you configure OSPF in your campus network? Where do you configure OSPF in your campus network? So we have the core layer. We have the core layer. We have the aggregation. So we have here we are using a switch. We have a core switch. Then we have the aggregation layer where we're having the aggregation switch, layer 3. And of course, we have the access layer. We have the access layer down here. So normally, The core switch and the aggregation switches will run OSPF to implement reachable routes on the campus network. So it is between the core and the aggregation layer where we configure OSPF so that we can be able to interconnect these different networks, right? Because you see, we are interconnecting them with different, these access switches. You see, we are interconnecting them with different layer 3 devices and interfaces, right? So normally, like each interface generates its own network. So we have a different network. So if we want Office Building 2 to be able to communicate with Office Building 1, here we have to implement a layer 3 routing protocol, or a routing protocol really. So one of the routing protocols we're going to be implementing here is OSPF. Is that clear? Yeah. So don't forget that. This is very important. Okay, so let's begin by looking at some of the basic concepts of OSPF. So the very first concept you're going to look at is the concept of area. I'm also excited that this time, at this level, they decided to introduce the concept of area a little bit deeper than it was in the previous course. So the OSPF area keyword identifies an OSPF area. So the area is considered as a what? Logical group. And each group is identified by what? An area ID. Is identified by an area ID. So by logical group, it means physically you can have routers at different parts of your network, but you can configure them to belong to a particular area. Are we together? Normally, these areas are given numbers from 0 onwards, but you must have area what? Don't forget that you must have area 0. Are we together? So you can't start creating from area 1, area 2, and you don't have area 0. You must have area 0. By logical group, it means we can create other groups. We can create area 1. We can create area 2. We can create area 3. The other thing you need to know is that all these areas must be connected to area 0. Any other area you create must be connected to area 0. And they'll have to communicate through area 0. So you cannot join the other areas together. And that is one of the strategies of ensuring that we don't have a loop. We don't have a loop, OSPF loop. So all of them have to communicate through area 0. So are you getting the point why you must create area 0? What I mean is you can create area 1, yes, and it will work. But when you want to expand, then what? Are you seeing the point? When you want to expand, then what? Because you cannot directly connect area 2 to area 1. There's a way you can do that. There's a way you can do that by creating a logical pipe to connect to area 0, but that is beyond what you're learning today. But if you do HCIP, you're going to learn how to do that. But at the moment, please understand that it is recommended that as you begin creating your SPF areas, you begin by creating area 0. So that when you create the other areas, you are simply going to interconnect them through area 0. Okay, so the other concept that is important in OSPF is the concept of the router ID. The router ID uniquely identifies the router in OSPF. Uniquely identifies. So router ID is simply router identifier. Anytime you hear ID, it means it has to be unique, right? It has to be unique. Now, the router ID can be please note, can be. It can be manually specified or automatically assigned by the system. So every router, please understand, every router in an OSPF area must have a unique router ID. It has to have a unique router ID. What is interesting about router IDs is that they are written just like the IP address in a dotted decimal format. So we can configure this router, for example, to have the router ID of 2.2.2, this one to have a router ID of 3.3.3.3. So we can't have R1 and R2 share the same router ID in the same area. No, it cannot happen. Don't forget that. So we are going to learn in the subsequent slides how the system automatically assigns a router ID in case you've not configured a router ID. But please note, it is recommended that you manually configure. It is recommended that you manually configure router IDs. Okay. So now the cost value. Very important that you understand this. Very important that you understand this. Very important that you understand this. That OSPF, let's read this together. OSPF, want to go? Yes, it uses costs. Now, OSPF enabled interfaces. Look here, OSPF enabled interfaces simply means that you have to enable each interface that you want to communicate via OSPF. Are you together? So OSPF enabled interfaces, when you're going to do configurations, you're going to see how we do that. OSPF enabled interfaces maintains a cost value. The default cost value uses what we call the reference bandwidth formula. It's called the reference bandwidth formula. They haven't mentioned it here, but I know reference bandwidth formula. So the reference bandwidth formula is like this: 100 megabits per second divide by the interface bandwidth. So that is how it looks like. So that's the reference bandwidth formula. Are we together? Okay, so let's do some calculation. What will be the cost of a link that is 100 of an Ethernet link? The link is 100 megabits per second. What will be the cost using that formula? If an interface can be able to transmit at 100 megabits per second, what would be the cost using that formula?
1 Mbps.
Exactly. So it's going to be 100 megabits per second divided by 100 megabits. So that's the interface bandwidth, which is going to give us a cost of what? Wonderful. What will be the cost of 1.544 megabits per second? It's going to be 100 megabits per second divided by 1 megabits per second, which is going to give us a cost of what? 64. If you do the division, it will come to around that, okay? Is that clear? Okay. So what will be the cost of a 1 gigabit? 1 GE, 1 gigabit? It will be 100 megabit per second divided by what? 1,000, right? Megabits per second. What is the result here? What will be the cost? It's going to be 0.1, eh? Yeah. So anytime you have anything that is less than 1, then the cost is, what do you call this in maths? A ceiling. The cost is taken upward to 1. So you can't have a cost of less than 1. Are we together? Yeah? I'm saying if the cost goes below 1, like 0.1, it's taken back to 1. Are we together? Is that clear? Don't forget that. So what will be the cost of 10 GE? 100 megabits per second divided by 10,000, right? Megabit per second. So this is going to be 0.01, which again is going to have a cost of 1. Is that clear? Yeah. So this is what we call, please listen, this is what we call the reference bandwidth formula. It's used to calculate the OSPF cost. The OSPF cost.
Sorry,
Now,
teacher, I have a
yes. Please ask.
That reference bandwidth formula, the
Uh-huh.
answer that we're putting, 164 and 1, in which value are they? In which units are they? Is it bits?
No. It's just the cost is just a number. It's just a number, so it doesn't have. What do we call it? It doesn't have an abbreviation. So just 1. It's just 64. Then,
Okay.
as you're going to see, we are going to be adding the cost of all the inbound interfaces along the path from the source to the destination. So once we do that, then we get the total. The path that gives us the least cost is the optimal path to the destination. So just a value, no, doesn't have any nini. Is that clear, Maurice? Is that clear?
Okay, that is clear, teacher.
Okay, thank you. Now, please look here. Is this the numerator? And this is the denominator. Is that so? Now, the default value of the numerator is 100 megabits per second for the reference bandwidth formula. That's the default value. But this is configurable, meaning this can change. You can configure this value to be a higher value. Are you together? Reason being, you don't want the cost of this link, the cost of this link to be the same as the cost of this link. Are you seeing that? With this formula, the cost of this link, 100 megabits, 1 gig, and 10 gig, their cost is the same. All of them have a cost of 1. So if you want to give them different costs, what do? You configure this from the default value of 100 to a higher value, for example, 10,000. Are you getting the point? So that now this one will have a cost of what? 100, right? 10,000 divided by 100. This one will have a cost of 10, right? And this one will have a cost of 1. Are you together? Yeah. If you visited with us the Huawei Training Center, I hope you remember that we were told we even have interfaces that do, as we go to the core network, we have interfaces that do even 400 megabits per second, right? 400 gigs, Yeah, 400 gigs. So that's why this value is configurable. Yes, the default is 100, but please remember you can be able to configure it. And I think we're going to see how to do that when we do the practical. Okay, so let me just clear this, then come back to this, that the cost of an OSPF route is the sum of all the inbound interfaces along a path from the destination network segment to the local router, So that's how we do that. So cost value of an OSPF interface, we've already seen how to calculate it. We've seen that a fast Ethernet will give us a default cost of 1, right? A gigabit Ethernet will also give us a default cost of 1, unless now we change the default value of the numerator of the reference bandwidth formula. Otherwise, both of them are going to give us 1. So each OSPF interface has a specific cost because of the particular bandwidth value. So when we are sharing LSAs, we also share our cost. Are you getting the point? Yeah, we share our cost when you're sharing the LSAs. Now, there's a concept of accumulated costs on an OSPF path that is used now to select the optimal path. So what we do is that in the routing table of R3, the cost of OSPF route to where? To this network. In R3, the cost of this is equals to what? Is 75. 75 meaning we start from here, all the inbound interfaces from the destination. So we add the cost of this interface here is 10. Are we together? The cost of this other interface here is 1. The cost of this interface here is 64. So 10 plus 1 plus 64, and then we get that the total cost for that particular path is 75. Is that clear? Wonderful. Okay. Interesting stuff. Interesting stuff. Please remember that OSPF have how many types? How many? It has 5 types of OSPF protocol packets. Protocol packet simply means messages. Messages that this particular protocol uses in order to achieve what we've discussed. Some part of what we've discussed so far: forming neighbors, calculating, sharing LSAs. Some of those things we've discussed. It uses 5 different types of messages, what we're calling protocol packets, in order to achieve that. The very first packet is called the hello packet. It's called the hello packet. Hello packet is easy to remember. The hello packet is used to discover the neighboring routers and is also used to maintain OSPF neighbor relationships. Also used to maintain OSPF neighbor relationships. So to discover how, when you configure an interface with OSPF, you enable OSPF on that interface, it starts sending hello packets. The destination IP address of that hello packet is the multicast IP address. I think it's 224.0.0.5 or .6, one of them. I can't remember clearly which one. So any other interface that has been enabled with OSPF is going to open up that hello packet. When it opens up that hello packet, it's also going to send back a hello message. Hello, I am this. When you're saying hello, you say, hello, I'm Kelvin. Hello, I'm Kellen. So when I'm talking about Kelvin, I'm talking about the router ID. So you say, hello, I'm 1.1.1.1. The other guy whose interface has been enabled with OSPF is also going to reply, hello, I'm 2.2.2.2.2. Okay, so hello packet. The other one is called the DD. DD. Please don't forget this one. DD. The DD is used to describe the summary of the local LSDB. The summary of the local LSDB. By local LSDB, it means we already have our own linked state database where we've saved details about our own interfaces. So it is the DD that is used to carry LSAs. Please remember that on the OSPF protocol types, we don't have a protocol type called, a protocol packet called LSA. We don't have a protocol. We don't have a protocol packet called LSA. LSAs are carried in the database description packet. So you'll most likely get a question, select one, which one among these maybe is not an OSPF protocol packet. And on that list, you're going to see LSA. So LSA is not an OSPF protocol packet. LSAs are carried using the DD packets, database description. So it's used to synchronize the LSDB of two devices. Then we have the link state request. It does exactly as the name suggests, is used to request a needed LSA from a neighbor. Request needed LSA from a neighbor. Now, you see the DD, which is the initial LSA, will carry a summary. By summary, it means we don't share all the details. For example, maybe we just share the IP address or the network address of that particular interface, so that guy checks, do I have this one in my LSDB? So if I don't have it, now I tell that guy, hey, send me more details about this guy. So he's now going to send more details, like maybe the cost and other details that we're going to see in a short while. So first, they'll share summaries. Then if you don't have that network or details about that interface, you now request. You request using an LSR. You request using a what? LSR, link state request. Then we have LSU, link state update. So after a router receives an LSR, it responds. It responds to the neighbor using an LSU. Then lastly, we have LSAC, ACK for acknowledgement, LSA, LSAC. So hey, it's important that I write these short forms. LSAC can be confused with an LSA. Anyway, so this one is just called hello. The next one is called DD, DD packets. So these are OSPF packets. OSPF packets. So we have hello, we have DD, OSPF packets. There are 5. 1, hello packet, then database description, then we have LSR, then we have LSA, LSU, I'm sorry. Then this one is normally called LSAC, so not LSA, LSAC. So those are the short forms for those particular packets. So acknowledgement is used to acknowledge that, hey, I have received the particular update, that I had requested for LSAC. So those are the 5 protocol packets that enable OSPF to achieve its purpose. Okay. So we want to see the OSPF tables. So we have 3 types. 3 types of OSPF entries. There are 3 types. So the first one is called the neighbor table. The neighbor table. Let me see if we can be able to go. The second one is called LSDB table. LSDB. Then the third one is called the routing table, OSPF routing table. So we have those 3. We have those 3 tables. we have those three tables, OSPF, OSPF. Let me just call them tables. Number one, we have neighbor. As you might have already guessed, this one saves the list of neighbors. So we said we start by forming neighbor relationships. So this will save the list of neighbors. Then you have LSDB table. Of course, this one will save the LSAs. Then you have the OSPF routing table. OSPF routing table. So those three. Okay, so let's begin with the neighbor table. So before SPF transmit links status information, OSPF have to establish neighbor relationships. So neighbors are established by using which packet? Using which packet? The hello packet. So OSPF neighbor table describe the status of the neighbor relationship between routers. The command that is used to display the contents of the neighbor table is OSPF, display OSPF peer. So let's look at this example. We have router 1 and router 2. The interfaces have been configured to exchange OSPF packets. The router ID of router 1 is 1.1.1.1, and router 2 is 2.2.2.2. So on router 1, if we do the command display OSPF peer, we are going to see that this is OSPF process number 1. You can create multiple OSPF processes, OSPF 2, OSPF 3. So this is OSPF process number 1. And the router ID of this router is 1.1.1. Then do you see it now displays a list of neighbors. So neighbors. Then which area are we in? We are in area 0. So that's why you see 0.0.0, area 0.0.0. On which interface? 1 gigabit Ethernet, 1/0/0/0, which is this interface here, on this interface. So you can see that it says 1/0/0 E'(S) neighbors, meaning these are neighbors that have been formed via that particular interface. So we can see that we have only one neighbor whose router ID is what? And we've connected to that particular neighbor via which interface? 10.1.1.2. Are we together? Yeah, so one of the other things we're going to be looking at, for example, is the state. You can see that here the state is full, right? So we're going to be seeing that. You can also see that we have the DR. We have what we call the DR here. And we also have the BDR. So who's the DR? 10.1.1.1. The BDR is 10.1.1.2. So we're going to understand in a short while what that means. We can also see what we call the priority, the master priority. And the priority here is 1, for example, right? Yeah, the priority of router 2 is 1. Okay, so we're going to understand all those in a short while. But in the meantime, just know that those are some of the details that you get when you look at the neighbor table. Using which command? Display OSPF peer. Okay, then the next table is the LSDB table. We know LSDB is used to store the LSAs. So, for example, in this example, the LSDB of R1 will contain how many LSAs? 3 LSAs. Remember, we also save our own LSAs, not just the other ones. So we are going to look at the type field, which is used to indicate the LSA type, and there are several LSAs types. We're not going to learn here about OSPF LSA types, but you can look at my videos on HCIP. We talk about that. Then we also have advertising router field, which is used to indicate the router that sends the LSA. So if you go to a router and you type an OSPF router and you type display OSPF LSDB command, then it's going to generate this particular table. So we have the same topology like we had in the previous slide. So on R1, if we type the command display OSPF LSDB, you can see that is OSPF process 1, router ID of R1 is 1.1.1.1. Then you can see the title of the table. It is the link state database of this router. Router ID. Okay, let me just skip that. So let's look at the first column. So the first column here is the type. So this is the type of LSA. Right now we can see that we have a router LSA and we have a network LSA, router and a network LSA. So as you might already have guessed, the router LSA is used to describe the router that advertises a particular the router that advertises a particular LSA. The network is used to describe that particular interface. So you can see that the advertising router here gives us the router ID of each of those routers that have advertised a particular LSA. So those are the important fields on the link state database. So display OSPF LSDB, right? Okay, then after that we have the what? The OSPF routing table, right? So OSPF routing table and the router routing table are different. Very important. They are different. So OSPF routing table will contain information such as the destination IP address, the coast, the next hop IP address, which guides packet forwarding. The command to use, display OSPF routing. Display OSPF routing. So on R1, if we do display OSPF routing, you can be able to see it is on OSPF process 1 with router ID 1.1.1.1. And you can be able to see that the routing table, OSPF routing table, has the destination column, which gives the network address and the mask. It also has the what? It also has the cost, right? Then it has what we call the network, OSPF network type. Again, we don't talk about this here. You can learn about it in HCIP. But what is important is the next hop. So if you want to go to this network, then send it to this guy. We also have the advertising router ID here, advertising router ID, and the area to which that router belongs to. So you can see, we can see that the total routing entries that we have here are 3 in this routing table. All of them are intra-area. Intra-area meaning they are within the area. All of them are in area 0. All these routes are in area 0. Otherwise, we have other area types, which we're not going to discuss here, like intra-area, ASE, and NSSA. Again, those ones are for HCIP. We're not going to discuss them here. Okay, so that's the overview of OSPF. Anyone with a question? Question. Are you understanding? Is it clear? Someone from online? Anyone with a question? Okay, wonderful. So
I have a question. Sorry, teacher.
Go ahead, Maurice.
Are we having a lab after this?
Yes, we're having a lab after this.
Okay.
After this one, we do the lab on OSPF.
Sorry, there's someone who wants to say hi to you. I don't know if you don't mind, please.
We don't mind. Thank you
Good
very much.
morning, Mr. Karis.
Good morning very much to you.
How are you?
Fine, thank you.
Okay,
Uh,
Alan here. I want to say hi to you.
Alan, Omwami,
Yes, yes.
Orie?
Yes, sir. Malay sana.
Good to hear you. Good to hear you from all the way.
Yeah, I see you on the 5 packets of SPF.
Yes, we are unpacking OSPF.
Okay, that is
Interesting
good. I
stuff here.
encourage everyone in the class.
Ah,
Okay.
thank you very much, Alan. Alan is a good friend to me, and he was my student in my first online class last year, and he has also done HCIP with me. Yeah, so he's working together with
Thank.
Maurice right now on a project in Angola. Yes, Alan, thank you so much. Glad to have you around. I hope you're also trying to catch one or two things. I
Yes,
know
yes,
you're
yes.
already an expert.
Yeah. Asante, asante.
Okay.
I'll be joining this one of the few instances I'll be maybe passing by to encourage the class maybe on
Yeah, yeah,
some
yeah.
area.
And in fact, Maurice can also tell you when we will be covering concepts such as the wireless LAN and
Okay.
also network programming, so that you can join him.
Okay, I will, I
Yeah,
will.
yeah, and also give him support in case he gets trouble with the labs or installing ENSP.
No problem, no problem. Thank you. Thank you. Let me not
Asante.
disturb the class for long. Okay.
Okay, thank you very much. Thank you. Good to hear from you, Alan. Okay, so uh, relationships. Relationships between OSPF routers. Relationships between two OSPF routers. We have two neighbor OSPF. We have two OSPF neighbor relationships. The first one is called the neighbor relationship. Neighbor relationship. Number two, it's called adjacent. Adjacent relationship. Neighbor relationship. Okay, let me just call it that relationship like that. So these are the two. These are the two relationships that we have. Mhm. Okay, so let's find out how it happens. So on a simple network, two routers are directly connected. When we enable OSPF on their interfaces, the interconnected interfaces, the routers will start to send and listen to hello packets. So after the two routers discover each other through hello packets, they establish a what? A neighbor relationship. The neighbor relationship can stop at the neighbor relationship, or it can go ahead up to the adjacent relationship. So the establishment of neighbor relationship is just the beginning. A series of packets such as DDD, LSR, LSU, and LSAC packets will be exchanged later, so after forming the relationship. When LSDB synchronization between two routers is complete, when you talk about LSDB synchronization, it means that we've shared all our interfaces, and now all our LSDBs are the same. Are you getting the point? So you said everyone is going to share with every other person. Yeah, so see, our LSDB is going to be the same. So that is what we call LSDB synchronization, because we all know about each other's interfaces. So when LSDB synchronization between two routers is complete and the two routers start to calculate routes independently, the two routers establish what? An adjacency. So if they're just two routers, they'll go all the way. They'll go all the way until they establish an adjacent neighbor relationship. Otherwise, as you're going to see, some routers also just end at the neighbor relationship. Are we together? Is that clear? Eh, but if they're just two routers, just two interconnected, then they're going to go all the way to adjacent neighbor relationship. Okay, so let's find out the process of establishing an OSPF adjacency relationship. How does it happen? So OSPF adjacency relationship establishment involves 4 steps. Establishing number 1, a neighbor relationship. Then you negotiate the master and slave status. So we're going to see what that means in a short while. Then you exchange LSDB information, and then you synchronize your LSDBs. So that is really how we do this. So again, just the high view is number 1, you establish a bidirectional neighbor relationship. So you've become neighbors. That's what we call the neighbor relationship. Then you negotiate who's the master and who's the slave. We're going to look into that. We're going to look at each of these steps, step 1, step 2, step 3, into it. Then we now start sharing LSAs, summary information. Then we start using LSRs and LSU and LSAC to request for routes that we don't have information on. Step 5 is performed separately on each device. So step 5 is using SPF, right, to calculate the routes. Okay. So let's look at step 1. So step 1 involves the process of establishing an OSPF adjacency. So we want to see. So we have these two routers, router 1 and router 2. This is not supposed to be area. This is supposed to be router ID. Sorry about this. This is not supposed to be area. It's supposed to be router ID. Similarly, this is supposed to be router ID. Okay, so when we configure OSPF, we enable OSPF on this interface on R1 and on this interface on R2. R1 will send a hello packet. Hello, I'm 1.1.1.1. I don't know who's on the link. Now, when R2 receives that particular hello packet, it's going to move from or transition from what we call the down state to what we call the init state. Init for initialize, right? Are you together? So now R1 is discovered and added to the neighbor list. So R2, it add R1 to neighbor list. Then the status of R1 in the neighbor table is init. Then after that, R2 will also send, hello, I'm 2.2.2.2.2. I found my neighbor 1.1.1.1. Now, when R1 receives a hello packet that has its own router ID on the neighbor list, then it will transit to what we call the two-way state. This two-way state is what we call the neighbor relationship. Two-way state. Then after that, R2 is discovered and added to the neighbor list. Because R2 discovered me, I set the status of R2 in my neighbor table to two-way, because this guy already knows me. Are you together? Yeah. Then after that, I'm going to send another hello packet. I am 1.1.1.1. I have a neighbor 2.2.2.2. So when this guy receives a hello packet from me with his own router ID on my neighbor list, it will now transit from the init state to two-way state. And that is what we call the neighbor relationship. Neighbor relationship. So here, OSPF, let me just call it states for lack of a better word, but we started from down, meaning that we've not enabled OSPF on these interfaces. So the OSPF state is down. After that, you receive a hello packet, you transit to init. You receive a hello packet with your own router ID on the neighbor list, you transit to what? 2A. And now you are neighbors. Now you are neighbors. So let me copy that. Okay. So step 2 and step 3. So here we're just looking at going forward. So after we have become neighbors, what else can we do? Now, okay. So here we are going to meet two. Oh, I thought I copied everything. Just a moment. Okay, I really don't understand. Okay, OSPF states. So we have down, init, 2A. Here we become neighbors. So we're going to see on this slide another state called extat and another one called exchange. So let's try and understand what that means. So R1 will send a DD packet. You remember DD? Database description. We said database description is used to carry the summary of LSAs, the summary. Now, this time, the content of the DD is going to be empty, meaning you're not carrying any summary information. What you do here, you just give that particular DD a sequence number, for example, X. You give it a sequence number, for example, X. Then you say, I'm the master, and my router ID is 1.1.1. Are we together? Now, when your neighbor receives the first DD packet, it transits from two-way state to X stat. Then this guy is also going to do the same thing. Generate a DD packet which is empty, give it a sequence number, for example, Y, then say, hey, I'm the master. You remember the master-slave relationship? This is where we want to form it. So this guy is also going to assume himself as the master. Hey, I'm the master. My router ID is 2.2.2. So when this guy, and please note, xstat simply means exchange stat, exchange stat. When router 1 receives the MTDD database description from R2, it transits to the exchange, state. Then R1 is also going to send, this is a summary of LSAs in my LSDB. So it's going to send a summary now, not an empty DD packet. And it's going to use the sequence number Y of that particular last message that it receives from router 2. So once it sends a summary LSA, then it transitions to the exchange state. When R2 receives a DD with some summary, it also transitions from extat to what? Exchange. After that, in the exchange phase, both ends exchange DD packets to describe the summary of their own link state advertisement. Just the summary. So you can see that now R2 is also going to send a summary of its LSAs. And the sequence number is going to be incremented by what? It's going to be incremented by 1. So y plus 1, like that, like that. Then this guy also sends, also increments +1, like that, like that. So by exchanging these summary LSAs, everyone will be able to know about the other person's LSA. Okay. Now, what is important here to note is that a master-slave relationship is selected based on the router ID. Based on the router ID. Are you seeing that we are no longer using the sequence number? We are no longer using the sequence number of this router, R1. But which sequence number are we using? The sequence number of R2, right? Yeah, we're incrementing the sequence number of R2 in subsequent DD packets that we exchange. You can see it's Y plus and not X plus. That is because R2 has been selected as the master. So how do we select the master? We select the master by comparing the router ID. So whoever has a larger router ID becomes the master. Becomes the master. Is that clear? And where does this happen? Where does this really happen? To know that you have indeed acknowledged that this is the master. Here, we send you, when we are sending you our first MTDDD, we send it to you, then now you compare your own router ID with this router ID. Then you see, this one has a better router ID. So now you start using their sequence number. So meaning that other person is the master. Are we together? Yeah. So during the exstart really, or exchange start, we are simply trying to create a master-slave relationship. That is what happens. Then during the exchange, we now start sending the summary LSA information. Okay. Yes, Jackson. Yes. Yes. Is there an instance where R2 will initiate the process of sending hello packets? So please remember, once you configure, you enable OSPF on an interface, it immediately begins sending out hello packets. Are we together? So if you configure R2's interface with OSPF first, then you go and enable the link on R1, most likely R2 is going to be the first one to send. So the process is going to be the same. They're still going to compare their router IDs to find out who's the master. Then whoever becomes the master, we're going to use now your sequence number. Of? Yes, exactly. So we're going to maintain the sequence number of Y, which maybe will be now the first hello packets. Are we together? Okay. Now, let's move on to step number 4, which is the last one. I'm not sure whether does this thing really, does it copy? Where are the others? Okay. So anyway, after exchange state, we go to what you call the loading state, and lastly we have the full state. Full state. When you adjust and see, when you're on the full state, then we say you're adjacent. OSPF state. So number 1, we say down, then init. After init, we have the we have the two-way. So here we say your neighbors. Number 4, we have the extract, then exchange. Okay. 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 So after you get into the after you are done with the exchange, you've shared all your summaries. Now you transit into the loading state. In the loading state, you're now sending LSRs for routes that you don't know about, not routes, but link states that you don't know about. So I want to request the complete information about this particular network, for example. So if this one receives that, also on loading, then it will reply with an LSU. This is the complete information about the requested LSA. Zip. Then this one will acknowledge. I confirm that I have received the LSU of the XXX LSA. Thank you. So these will continue. This will continue between the two routers. You look at the summary, I don't have information about this one, you request it, you acknowledge it, and so on and so forth. So this will go on until now you have information about each other's LSDB, full information. And now that state is what we call, what? The full state, the full state. When you're in the full state, then we say that your neighbor relationship is the adjacent neighbor relationship. You formed an adjacency. You formed an adjacency. Yeah. Okay, let me try and move a little bit faster. Okay, so the OSPF, let's look at some of the fields of the OSPF neighbor table in detail. So if you use the command OSPF, display OSPF peer, then you're going to get the process and the router ID. We've already talked about that. Then the neighbors. So in this particular example, we're looking at R1 and R2. On those interfaces, router ID of R1 and router ID of R2 is as we can see there. Uh-oh, I think my mouse, my battery is kaput. Wireless mouse. I don't like using the touchpad. Let me see whether I'm going to be able to use it. Okay, so area here simply shows the area where you are. Interface, the interface that has been interconnected. Remember here we are on R1, right? Yeah, so we've interconnected on this particular interface. This one here, this one, this one. Okay, so we can see area. Let me just. Okay, let me just keep this in the meantime. But you can see that the state, what is the OSPF state for the two routers? You can see it's full, right? Yeah, it's full, meaning they are formed an adjacency. Now here, mod, what does it say? Neighbor is Neighbor is what? Master. Simply meaning that this particular neighbor is the master. This guy is the master. This one, whose address is 10.0.1.1.2. So this guy is the master. And then you have the DR. We have the DR and BDR. DR is designated router. BDR is backup designated router. So we're also going to see how the elections are done for those two routers. Okay. Let me just, for example, okay, let's just move on. So those are some of the okay. So now let's look at the OSPF network types. So before learning about DR and BDR, we need to understand the OSPF network types. Normally, the network type will default to a particular type depending on the interface, depending on the type of interconnection that we have between the routers. Now, it is important that we understand this because it affects the OSPF operations on each of those interfaces. For example, it might determine how we are going to be sending OSPF packets, how we're going to be sending them. I already said that like the hello packet is sent on a multicast IP address, but what if a certain type of connection does not support multicast? So how then do we send the packet? Number two, it also determines whether we are going to select a designated router and a backup, whether we're going to elect, not select, a designated router and a backup designated router. So that's why it's important to understand these network types. So the default OSPF network types of an interface depends on the data link layer encapsulation. How do we encapsulate the data at the data link? And also this is determined by the type of link that we use. So as shown in this figure, how many network types do we have? OSPF network types? We have how many? We have 4. We have 4 network types. Don't forget these OSPF network types. Can I just say 4 OSPF network types? So the first one is called broadcast network. It's also called broadcast multi-access network, BMA, broadcast multi-access network. The second one is called non-broadcast multi-access. Or simply NBMA. The third one is called point to multi-point network. And lastly, we have point-to-point network. So these are the four network types. This one, short form is P2MP. This one, short form is P2P. Let me just call this one broadcast multi-access. So those are the 4. These are the 4 OSPF network types. So if you want to see these network types on a router, you can be able to do so by going into an interface You go into an interface, for example, in R1 here, then you type OSPF network type, network hyphen type space question mark. So you're going to see a list. You're going to see a list of all the possible options that you have. Now, while using certain interfaces will default to particular network types, you can also change, you can also configure. And of course, the command to configure a particular network type is this one. You go to an interface, then you use OSPF network hyphen type, then for example, you say P2P. Even though it's a broadcast network, you can change it to P2P, you can configure it. So the network type, OSPF network type is configurable. That is what I want you to remember from here. Okay. So let's have a look at them. So network types of OSPF at both ends of the link must be the same. Very important. That means that the network type you configure on this interface must be the same as the network type you configure on this interface. Is that clear? They must be the same, the network type at both ends. Otherwise, the two interfaces cannot establish a neighbor relationship. So an OSPF network type can be manually changed on an interface to adapt to different network scenarios. So I've said you can configure, you can change, you can manually change. So for example, you can change a broadcast network type to point to point. Point to point. So one of the scenarios where we might need to change a broadcast network type to point, for example, is when we don't want an election to occur. So in broadcast network types, we have an election. We elect a BR and a BDR. In P2P, we don't elect because we just have two routers that are directly connected to each other. That's what we call a point-to-point network. So we don't need a DR and a BDR. So sometimes when we are connecting to an ISP, we're having a direct connection to an ISP, we don't want an election between our router and the ISP's router to have a DR and a BDR. So even though maybe we've connected through Ethernet, which defaults to broadcast network type, we can configure it to a P2P link network, OSPF network type, just to ensure that we don't have an election. Are we together? Because the election will be unnecessary. We don't need it. Okay, so let's have a look at this. So point-to-point network, P2P. So with P2P, point-to-point, it indicates that only two network devices can be connected on a link, directly connected. So a typical example of PP is a PPP link. So normally, when we use the point-to-point protocol for the data link layer or layer 2 encapsulation, then that particular OSPF network type will by default results to P2P. And most of the time, we use PPP when we are also connecting via the serial interfaces. Are we together? Yeah. So when we connect two devices together, two interfaces via a serial cable, and we use PPP encapsulation point-to-point protocol, then that will default to a point-to-point network, OSPF network type. Otherwise, when we interconnect using the Ethernet interfaces, and we use Ethernet at layer 2 for encapsulation, then the network type will default to BMA, broadcast multiple access or multi-access. So BMA is also called what? Just broadcast. So it refers to the environment that allows multiple devices to access and support broadcast. So what that means is that on a BMA, you can be able to send broadcast packets. You can be able to send broadcast packets. For example, if you're having yes, for example, like this connection, if you send a broadcast packet to this switch, it's going to send it to this one and to this one. So it supports broadcast. So a typical example is an Ethernet network. So an interface uses Ethernet encapsulation. Then the default network type is BMA. Okay, then we have non-broadcast. So even from the name you can tell that this one does not support broadcast. So you cannot be able to send broadcast. One of the technologies that we are no longer learning, but we have notes for this, is frame relay. So normally frame relay uses what we call virtual circuits to interconnect. So we have what we call a frame relay switch. Then you have to create pipes to and fro like that. So for sending, for example, and receiving. So really, you use what we call virtual circuits, and it cannot support broadcasts. Okay, and then the last one is point to multipoint. So point to multipoint network is formed by bundling endpoints of multiple point-to-point links. So when you have multiple point-to-point links, then you have point to multipoint. So what that means is that you've interconnected these two. You have interconnected these two through a point-to-point, and here, then here, like that. So for example, you can use this kind of thing when you want all the branches to connect to the headquarters. So you can have such like a topology. So that is what we call the point to multipoint. Now, no link layer protocol is considered as point to multipoint network by default. So this type must be manually changed from another network type. So don't forget that there is no layer 2 encapsulation protocol that will default to point to multipoint. You have to manually configure it. Okay. So those are the 4 network types. So later on, I'll tell you where elections occur and where elections don't occur in each of those network types. Okay. Actually, it's not far from now. It's just now. So we have what we call multi-access networks. Multi-access networks such as BMA and NBMA and NBMA. So Ethernet is a typical broadcast multi-access network. By multi-access, really, what we mean by multi-access is this. I think when you're going to learn about NINI, maybe we might understand better. But you see, like here, we are having a bus topology, right? And we have the bus here. So anyone can access this link at any given point. Anyone can access it at any given point. If I want to send data, I can access it at any given point. So that is what we call multi-access. Multi-access. So we have a way of controlling who can access when in order to avoid what we call collision. I think we're going to learn about that in the next topic. So On multi-access networks, if each OSPF router establishes OSPF adjacencies with all the other routers, then we're going to have a problem. We're going to have a problem. One problem is that we're going to have excessive OSPF adjacencies on the network, which will increase the load on the devices and also the number of OSPF packets that are flooded on the network. So if we're going to have everyone creating adjacency with every other person, then we are going to have a lot of adjacencies. And that means that each of these routers is going to do a lot of calculation. So it's going to take a toll on the CPU. And because of all the messages we are going to send, we're also going to waste bandwidth, because everyone is sending hello to every other person. So we're going to waste bandwidth. So for that reason, remember, this is the background of the DR designated router and backup designated router. So for this reason, on multi-access networks, what do? We have three types of OSPF routers. We have three types of OSPF routers. So three types of OSPF routers. That is on multi-access networks. So we have what you call the designated router. Then we have backup designated router. And lastly, we have what you call DR other, or designated router other. So the reason as to why we're doing this, having designated and backup designated, is so that all the other routers establish adjacencies only with the DR and the BDR and not with each other. So DR others do not establish OSPF adjacencies with one another. So their relationship ends at the neighbor relationship, the two-way state. Are we together? DR other, their relationship with each other end on the neighbor relationship. They don't form adjacencies. They don't exchange LSAs. You only exchange LSAs with the DR and the BDR. So the BDR monitors the status of the DR, the purpose of the DR. Why do we have the backup DR? Monitors the status of DR, takes over the role of the DR if the DR fails. Are we together? Are we together? Now, how do we elect? Oh, I'm still trying to use my dead mouse. DR election rules, or can we say DR and BDR? Election rules. So highest priority. So the router priority. Whoever has the highest priority becomes DR, is elected DR. Second highest becomes BDR. The default router priority is 1, but the router priority is configurable so that you can choose to select which router becomes the DR. So you can configure the router priority, but default value of the priority is 0. In case all of them have the same, router priority. For example, you've not changed the router priority of any router. Then highest router ID is going to be used. So this is the other purpose of the router ID. So router with the highest router priority is going to be used. Lastly, DR is non-preemption. The DR is non-preemption. That means that once the DR has been elected, if you add to the network another router, with a better router priority or with a better router ID, we are not going to carry out elections. Are we together? Just like our national elections are non-preemption. If we've elected Raila Amolo Odinga as the president of Kenya, and Ruto comes up with the bottoms-up strategy and convince us that this is the best strategy, we are not going to carry out elections just because this one has better promises and strategies. No. They have to finish their term. So that is what we call non-preemption. Don't forget that. Expect a question about that in the exam. Then, of course, BDR takes over. BDR takes over if DR fails. So don't forget that. Okay. So please note, you'll only have one DR, one BDR, right? Then all the other routers are DR others, DR others. Then look, you only form adjacencies with who? With the DR and the BDR. So look, how many adjacencies have we saved? This guy will also have formed adjacencies with who? With that one and that one. Are you seeing that? So we've saved those two. What about for all the others? There's a formula for calculating that, which I'm forgetting. But are you seeing that we've reduced the number of adjacencies? We've greatly reduced. So everyone just share with DR and BDR. We are going to get your LSAs from DR and BDR. So by that, we reduce the load of our, in terms of even storage and processing, and we also reduce the bandwidth usage of our network. Okay, so now let's look at the OSPF single domain, OSPF domain and single area. Let's find out what this is. So domain is a network that consists of a series of contiguous OSPF network devices that use the same, what? That use the same policy, just like an autonomous system. So we are using the same policy. So OSPF routers flood LSAs in the same area. To ensure that all routers have the same understanding of the network topology, LSDBs need to be synchronized within what? Within an area. If there is only one OSPF area, the number of routers increases with the network scale. That is, we expand our network, we add more routers. These will then cause the following problems. Number one, the LSDB will become larger and larger, thereby increasing the size of the routing table. A larger number of router resources then will be consumed, and device performance will deteriorate and thereby affect the data forwarding. So it is also difficult to calculate routes based on a very large LSDB. Remember, we create routes by using the SPT, the spanning, the shortest path tree, where we make ourselves the root of the tree. So if we have so many routes, then this tree is going to be quite complicated, right? And thereby we are going to use more CPU resources to calculate it. Another problem, in case we have a change in the network, you remember what Leo asked? When you have a change in the network, we have to recalculate the tree, right? Yeah, so anytime we have a change, we have to do LSA flooding and we have to do the recalculation of the entire network, which brings heavy load to the network. Don't forget these problems. Expect a question in the exam on this. So for this purpose, OSPF supports what we call multi-area, so that instead of adding all the routers in the same area, we now add other routers on other areas, so that we can reduce the size of the LSDB. That's the purpose of multi-area, and we can allow the network to easily scale. So multi-area OSPF. So OSPF introduces this concept. The domain is divided. So that is like the network of the ISP, divided into what? Multiple areas in order to support larger scale networking. So multi-area design reduces the flooding scope of LSAs, because you can only flood LSAs within a single area. It can't go outside your area. This effectively controls the impact of topology changes within the area, thereby optimizing the network. Routes can be summarized at the area border. At the area border, the routes can be summarized to reduce the size of the routing table. Also, multi-area improves network scalability and facilitates large-scale network construction. So instead of just having all the routers in area 0, you have area 0, then you have area 1, area 2. If you want more routers, you create an area 3, and so on and so forth. Okay, so let's talk about a few things here. OSPF area types. So number one, we have what we call the backbone area. Normally area 0 is what we call the backbone area. Then the other ones are referred to as non-backbone area. So these are other areas. So don't forget that. So area 0 is what we call the backbone area. Now, to prevent loops between the areas, non-backbone areas cannot be directly connected to each other. They cannot be connected to each other. That's why you can see here. So what we're saying is that you can't connect area 1 to area 2 like that. So don't do this. Otherwise, you might have loops. So what you do is you connect these areas via the backbone, and communication has to be through the backbone, through area 0. Okay. So we have several types of routers when it comes to OSPF multi-area. Specifically, there are 4 types of routers. The first type is called the internal router. So with the internal router, a router is called internal router if all its interfaces are within a single area, like this router here in the backbone. or this one here in area 2, or this one here in area 1, internal router, all its interfaces belong to the same OSPF area. Then the second one is what we call the ABR, or area border router, ABR. And ABR, on the other hand, is used to interconnect two areas. So one interface is in one area, the other interface belongs to another area. But at least one interface must belong to the backbone area, right? So we've said we interconnect them through what? Through area 0, right? Yeah, so the area border router, one of its interface must belong to the backbone area. So this is an ABR. This is also an ABR. Then routers in the backbone area are normally called the BR, backbone router. So all these routers in the backbone area, in area 0, they are called BR, backbone router, because they are in area 0. So a backbone router has one of its interfaces in the backbone area. Then lastly, we have the ASBR, Autonomous System Boundary Router. Autonomous System Boundary Router. ASBR connects you to another AS, to another autonomous system. So this is an ASBR, this is an ASBR, Autonomous System Boundary Router. So those are the four types. Those are the four types of OSPF routers. Okay. Haya, tusonge mbele. So OSPF, single area and multi-area networking, we just want to see the application scenarios. So networks that have a limited number of routing devices, like what we're having here, can simply use a single area. So all the routers are in area 0 because we just have a few number of routing devices. So if you have a few number of routing devices, then they can all belong to area 0. Other a large sorry, my mic had changed. Okay. Are you able to hear me? Those that are online?
Yeah, we are hearing you, Malimu.
Yes.
Wow, wonderful. Thank you. Okay, so otherwise, if you have a large number of routers in your network, if you have a large number, then you have to use multi-area deployment. Multi-area. So how do you do that? On the core layer, you configure the core layer routers to be in. Oh, something is happening with my mic. Let me just sort it out. Okay. Then next, just a moment. Okay, so on the aggregation layer, you can now be able to create other areas and interconnect them together via area 0. So is that clear? Kimeeleweka? The application. Okay, so that is it about the working mechanism of OSPF. Let's now see how to configure. Yes, Kellen? This? Come up again? The aggregation layer. Sorry, can you be loud enough? Area 0. Yes, you configure the core layer routers in area 0. So you now divide the aggregation layer into several areas. Remember that is where OSPF ends, because in access layer we don't configure a routing protocol, right? Because you're using layer 2 communication, layer 2 switches. So for this network to be able to expand, then at the core layer, you configure those routers at the core layer to be area 0, because all the aggregation layer routers or layer 3 switches are going to connect to these routers. So these other routers now can belong to other routers, to other areas, OSPF areas. So that is what is being shown there. Okay, so let's look at how to configure OSPF. Quite interesting stuff here. Okay, so step number 1 on system view, we have to create and run an OSPF process. How to do that? We use the command OSPF, then the process ID. You can give it a process ID or fail to do it. If you fail to do it, the default process ID of 1 will be used. Then after that, which is also optional, you can type the router ID. Router ID, then you give it a particular router ID. So just as an example, quickly, so you do something like, let me just use that. So for example, we are in R1, so you type OSPF, then 1 for the process ID. So if you want, you can press enter here and you go to the next step. Otherwise, you can also configure a router ID manually using that command. Then 1.1.1.1. Are we together? Otherwise, you can also eliminate the process ID there. So if you do that, simply going to go to OSPF1, which is the default process ID. So that's how you configure that. Now, in case, did I mention that in case you don't configure a router ID manually, what happens? Automatic router ID. What does the router do? It picks the largest IP address. It picks the largest loopback IP address. Remember, we said that one of the uses of logical interfaces, and specifically the loopback IP addresses, is that it's used by protocols such as OSPF. So this is how OSPF picks. This is how it uses the loopback addresses. So because the router ID has the same format as an IP address, so it simply picks the largest among the loopback addresses. Otherwise, it picks the largest interface, physical interface IP address. So that's how, if you don't configure the router ID, that is how it's going to happen. But it is recommended that you configure the router ID manually. Okay, so let's go on to the next step. The next step is area. So use the keyword area and then area ID. The area can move from 0 to that particular number. So area 0, or area 1. So that's how you create an OSPF area and enter now into the area view. So area view, this is how you know that you're on the area view. Normally the number is that, like that. With the OSPF area, you can give it an integer or you can give it a dotted decimal number. I think there are those two options. Please read about that when you find time. Then after that, step number 3 here is on OSPF area view, we can now advertise the interfaces. So specify the interface that runs OSPF. Oh, yes, we specify the interface that runs OSPF, not advertising, but specifying the interface that runs OSPF. How we do that is by using the network command. So network, then the network address of that particular interface, then the wildcard mask. The wildcard mask is the reverse or the inverse of the mask, the normal mask. So if the mask has 24 ones, 24 zeros, 24 ones and 8 zeros, you change the ones to zeros and you change the zeros to ones. That's what we call the wildcard mask. So for example, we might type the command network 192.168.0.0. Sorry. Or .1.0, like that. So if we have this and it's /24, the wildcard mask is going to be 0.0.0.255. So this is /24. We simply change the ones to zeros and zeros to ones. So that's what we call a wildcard mask. So we use the network command. We use the network command to advertise the interfaces. So you simply enter the network address of the interface and the wildcard mask. Okay. After that, we can set the interface cost. We can set the interface cost so that we can choose, we can decide to manually choose the path that is going to be added to the routing table. So that maybe we can share bandwidth or something. So if you don't want the reference bandwidth formula to be used on an interface to calculate the cost of that interface, you can go into that interface, for example, G1/0/1. Then you use the command OSPF space cost. Then you enter a value between 1 and 65,535. Otherwise, you can change the bandwidth reference value. You remember what was the default bandwidth reference value at the numerator? It was 100, right? Yeah, but we said it's not very accurate because it will give the same value, cost value, for a 1 gig and a 10 gig and 100 Mbps interface. So if you want to change this to a bigger value, the command is this. You go into OSPF view, you just type OSPF1, enter. Then you type the command bandwidth reference, then you enter a value like 10,000. So if your maximum, if the maximum interface you have maybe is 10 gig, you can give it 10,000. If it's 400 gig, you can give it 400,000, for example. Okay, then we can also set the priority of an interface. So that router can be elected as the DR. So we might want to do this in scenarios where we want a more powerful router to be elected as the DR. So to do that, you go into the particular interface, then we do OSPF. The command is DR hyphen priority. Then we enter a priority value. The value ranges from 0 to 255. 255. And already we talked about this, that in the election rule, the higher the DR priority, then the router priority, then that router is going to be elected as the what? Is going to be elected as the DR. So we have a configuration example for OSPF that we want to go through here together before we come back and do the lab. So the description is that we have 3 routers. So we have R1, R2, and R3. They are connected to 2 different networks, which have been which are going to be configured as loopback interfaces. So simulated by loopback 0 on both of them. So we're going to create loopback 0 on both of them and give them this IP. So we want to use OSPF to implement internetworking between the 2 networks. That means that we want to configure OSPF so that we can be able to ping from 1.1.1.1 to 3.3.3.3 and vice versa. So R1 and R2 belong to area 0. Then R2 and R3 belong to area 1. So what is the name of this router R2? It's an AB. It's an ABR, right? An area border router. Okay, so the configuration steps. Step number 1, we configure the IP addresses and the mask, and we also configure the loopback interfaces, right? Loopback 0. Then after that, we configure OSPF. And lastly, in the configuration process, we verify the results by maybe using a ping. Okay, so let's do that. So I'm not going to go through this because we talked about this in the previous lab about configuring interfaces. So you simply go into the interface view, you give it an IP address and the mask using that command, just like that. Okay, so let's go on to configuring OSPF. So in configuring the OSPF, the procedure is to create and run the OSPF process. So here we are configuring the OSPF process 1, and we're also configuring the router ID of R1, right? Then we go ahead and specify the area 0. Then we advertise the networks or the interfaces using the commands. Look here. So we have what? We have those 2 networks, right? So see, we are advertising this interface, and we're also advertising this interface. You understand why the wildcard mask here is 0.0.0.0? You understand that? Because we are converting 32 ones into zeros, right? You understand why here it's 0.0.0.3? Huh? Why 3? It is /30. So why 3? What will /30 give us at the very end? It will give us how many ones? 1, 2, 3, 4, 5, 6, 7, 8. So we remove 2 so that we have zeros, right? 2 zeros on the last part, right? So you have 31s. Yes? Yeah. If we convert this into the inverse, we have this, right? If we convert 1, 1 into binary, we get what? Into decimal. You get 3, right? Yeah, so that's why the mask here is 3, right? Don't forget that. Okay, so we are supposed to do that on router 2 and router 3. So just the same thing. So in router 2, again, I think it's important that I mention this. In router 2, we have to create two linear. We have to create two areas. So first of all, we create area 0. Then we advertise the interface that is in area 0, this one. So we use the network command and the inverse mask. Then we create area 1. Then we use the network command and the inverse mask. Is that okay? Then on R3, we only create one area. So OSPF1 router ID, area 1. Then we advertise the loopback interface and the physical interface. Is that okay? Using the network command. So you see, in link state routing protocols, we really advertise the link state. Okay, so now let's go ahead and confirm, verify our configuration. How to do that? We can display the OSPF peer, or the OSPF neighbors by using the command OSPF peer brief, display OSPF peer brief. So it's going to tell you that here, right now we are in R2. Please remember we are in R2. We expect that R2 has formed a neighbor relationship with R1 on area 0 and with R3 on area 1. So let's find out that and see that the router ID is 2.2.2. We can see that on area 0, we have formed a neighbor relationship with this interface 000, neighbor router ID 1.1.1. The state is full. We can see that on area 1, we have formed a neighbor relationship with that interface, router ID 3.3.3.3, and the status is full. Okay. So the other way to verify is to check the IP routing table. So display IP routing table. Do we have these networks installed in the routing table? Oh yes, we have 3.3.3. You can see that on the proto field, we have learned this through OSPF. The default preference value for OSPF, what? 10, right? And then we can go ahead and ping using the -A command to specify option, -A option to specify the source. So ping -A 1.1.1.1 space, then 3.3.3.3. So when we do that, we are going to get replies from this guy, meaning that now we are able to ping the loopback interfaces of these two routers. So OSPF has been used to automatically generate these routes. So please know that how we verify that a particular protocol is working is by number one, displaying. We display the tables to find out. Like here, we've displayed the neighbor table. We've displayed, you can actually even display the LSDB. You can, all the tables, the OSPF routing table, display OSPF routing. Or you can display the routing table to see whether the route has been added to the routing table. Otherwise, you can also use ping. You can also use transat to verify the connection. Okay, so please find some time to discuss these two questions. Find some time to discuss these two questions. If you have a problem, you can let me know so that I can support you. Just to mention here, OSPF has more interesting details. Look here, has more interesting details such as LSA types, how we do calculate SPF, special areas, We saw areas like inter-area, NSSA. So for more OSPF information, please continue to HCIP.com certification courses. You can watch my HCIP videos. I have already covered that in depth. What's more, on HCIP, you can also learn about ISIS. So on my channel, YouTube channel, Teacher Karis, I have videos on ISIS. Thank you very much, ladies and gentlemen, for your active participation and questions. Asanteni sana. Now we do the lab for OSPF. Thank you.